You think gravity is a force. You think the earth pulls you down. You think massive objects attract each other through some invisible tug across empty space. That's what Newton said. That's what you learned in school. And for 250 years, it worked perfectly. Planets orbited. Apples fell. Engineers built bridges. Everything made sense. But it was wrong. Completely, fundamentally wrong. And Einstein proved it in 1915 with an idea so radical, so bizarre, that even today most people can't fully wrap their heads around it. Gravity isn't a force at all. It's geometry. It's the shape of space and time itself. And once you understand what that actually means, you'll never look at the universe the same way again. Let's start with Newton, because that's where the confusion begins. Isaac Newton, sitting in his garden, watching an apple fall, or so the story goes. He has this brilliant insight. The same force that pulls the apple down also keeps the moon in orbit. Universal gravitation. Every mass in the universe attracts every other mass. The force depends on how massive the objects are and how far apart they sit. Double the distance, the force drops to a quarter. Triple it, 1/9, an inverse square law. Beautiful, simple. And it works. Newton could predict planetary orbits with incredible accuracy. He could calculate tides. He could tell you exactly where Jupiter would be in 100 years. For practical purposes, Newtonian gravity is still good enough. We use it to launch satellites. We use it to navigate spacecraft. It's not that Newton was stupid. He was a genius. But he knew there was something missing. He knew his theory had a problem. Here's the problem. Newton's gravity acts instantaneously across space. The sun pulls on the Earth right now. If the sun suddenly vanished, poof, gone. Newton's equations say the Earth would immediately feel it and fly off into space. No delay, instant communication across 93 million miles of empty void. How? Newton had no answer. He wrote in his Principia that he could describe how gravity behaves, but not what gravity is. He admitted he was inventing no hypotheses about the mechanism. He just gave you the math, and the math worked. So everyone used it. But deep down, it bothered people. How does the sun reach across empty space and grab the Earth? What's doing the pulling? And why does it happen instantly? Newton couldn't say. He just said, that's how it is. Shut up and calculate. Fast forward to 1905. Einstein publishes Special Relativity, and immediately there's a problem. Special relativity says nothing can travel faster than light. No object, no force, no information. The speed of light is the ultimate speed limit of the universe. But Newton's gravity is instantaneous. If the sun disappears, Earth should feel it right away, according to Newton. But relativity says no. The information that the sun is gone can't travel faster than light. So there should be an 8-minute delay. Light takes 8 minutes to travel from the sun to Earth. Gravity should take the same time. But Newtonian gravity doesn't have any time delay built in. The equations don't account for it. So one of two things must be true. Either special relativity is wrong or Newtonian gravity is wrong. And Einstein knew relativity was right. The experiments confirmed it. Time dilation, length contraction, E equals mc squared, all verified. Which meant gravity had to be rebuilt from the ground up. Einstein spent 10 years on this problem. 10 years. He called it the happiest thought of his life when he finally figured it out. And here's the thought. Imagine you're in an elevator. The cable snaps. You're in free fall. What do you feel? Nothing. You float. You're weightless. If you let go of your keys, they don't fall to the floor. They float next to you. Both you and the keys are falling at the same rate. So relative to each other, there's no motion, no force. If you didn't look out the window, you couldn't tell you were falling. You'd think you were floating in deep space, far from any gravitational field. Now flip it. Imagine you're in a spaceship accelerating through empty space. No planets, no stars. Just you and the rocket engine pushing you forward at a constant acceleration. What do you feel? Weight. You feel pressed into the floor. If you drop your keys, they fall. From your perspective, it's identical to standing on Earth. The floor pushes up on your feet. Objects fall when you release them. You can't tell the difference between being in a gravitational field and being in an accelerating reference frame. This is the equivalence principle, and it's the key to everything. Einstein realized something profound. If you can't tell the difference between gravity and acceleration, maybe there is no difference. Maybe gravity isn't a force at all. Maybe when you stand on the ground, you're not being pulled down by some mysterious force. Maybe the ground is accelerating up into you. But wait, how can the ground be accelerating up if you're not moving? You're standing still. The earth isn't getting bigger. This is where Einstein's genius kicks in. He said space and time aren't fixed. They're flexible. They can curve. They can bend. And massive objects like the earth curve the space and time around them. You're not standing still. You're trying to move through time in a straight line. But the earth has curved the geometry of space-time around it. And that curvature is what you experience as gravity. Let me try to make this concrete. Imagine space-time as a flat rubber sheet. Now put a bowling ball in the middle. The sheet sags. It curves down around the ball. Now roll a marble across the sheet. It doesn't travel in a straight line anymore. It curves toward the bowling ball. Not because the bowling ball is pulling it, not because there's a force reaching out and grabbing it, but because the sheet itself is curved. The marble is just following the straightest possible path through the curved geometry. In space-time, we call that path a geodesic. And that's what you're doing right now. You're following a geodesic through curved space-time. The earth isn't pulling you down. The earth has curved space-time around it. And you're trying to move forward through time in a straight line. But the curvature redirects you. The surface of the earth interrupts your geodesic. And that interruption is what you feel as weight. The ground is pushing up on you. You're not falling. The ground is accelerating into you. That's gravity. Now, you're probably thinking, this is just a different way of saying the same thing. A metaphor, a visualization trick. It's not. This is the actual geometry of the universe. Einstein wrote down the equations that describe exactly how mass curves space-time. They're called the Einstein field equations, and they're brutally difficult, 10 coupled nonlinear partial differential equations. But they work. They predict things Newton's gravity can't explain. Mercury's orbit, for example. Mercury orbits the sun in an ellipse, but the ellipse itself rotates slowly over time. The point of closest approach to the sun shifts slightly with each orbit. This is called perihelion precession. Newton's gravity predicts some of it. The gravitational influence of other planets tugs on Mercury and causes some precession, but not all of it. There's a tiny discrepancy, about 43 arcseconds per century. For 50 years, astronomers had no explanation. Some thought there was an undiscovered planet inside Mercury's orbit. They even gave it a name, Vulcan, but no one ever found it. Because it doesn't exist, Einstein's equations predicted the exact amount of precession, 43 arcseconds per century. No fudge factors, no invisible planets. Just the curvature of space-time near the Sunday. That was the first major confirmation that general relativity was right. The second came in 1919, a solar eclipse. Einstein's equations predicted that light passing near the sun should bend, not because the sun pulls on the light. Light has no mass. But because the sun curves space-time, and light follows geodesics just like everything else. If space-time is curved, light curves with it. The effect is tiny. But during a solar eclipse, you can see stars that are directly behind the Sunday. If light is bending, the stars should appear shifted from their normal positions. Arthur Eddington led an expedition to measure this during the 1919 eclipse, and he found exactly what Einstein predicted. The light bent. The stars shifted. General relativity was confirmed. Einstein became a celebrity overnight. Newspapers around the world ran headlines. Newton overthrown, and it was true. Gravity wasn't a force, it was geometry. But here's where it gets really strange. If gravity is just the curvature of space-time, then time itself is affected. Time runs at different rates depending on how curved space-time is. The stronger the gravitational field, the more space-time is curved, and the slower time flows. This is called gravitational time dilation, and it's not a metaphor, it's real. measurable. If you put one clock on the ground and another clock on a mountaintop, the one on the mountaintop ticks faster. Not by much, but faster, because it's farther from the Earth. Space-time is less curved up there. Time flows faster. We've measured this. Atomic clocks are accurate enough to detect the difference, and it matters. GPS satellites orbit at about 20,000 kilometers above the Earth. Up there, space-time is less curved. Time flows faster, about 45 microseconds per day, faster than on the ground. If we didn't account for this, GPS would be off by miles within a single day. Every GPS satellite has to correct for gravitational time dilation. It's not optional. It's built into the system. Your phone right now is compensating for the fact that gravity bends time, not because engineers believe in Einstein, but because if they don't, GPS doesn't work. Let's push this further. What happens near a black hole? A black hole is a region where space-time curvature becomes so extreme that even light can't escape. The boundary is called the event horizon. At the event horizon, space-time is curved so much that all future directed paths point inward. There's no way out. Not because something is pulling you in, but because the geometry of space-time itself has been bent so severely that outward no longer exists inside the horizon. And time stops. From your perspective, falling into a black hole, everything seems normal. You cross the event horizon, you keep falling, but from the perspective of someone watching you from far away, you never cross. They see you slow down as you approach the horizon. They see your clock tick slower and slower. At the horizon, your clock stops. Time dilation becomes infinite. You freeze forever. Not because you stopped moving, but because the curvature of space-time has bent time itself into a standstill at the horizon. This isn't theory. We've observed matter falling into black holes, and it behaves exactly as general relativity predicts. Now let's come back to Earth. Literally. You're standing on the ground right now. You feel weight. Newton would say the Earth is pulling you down. But that's not what's happening. The Earth is curving space-time around it. You're trying to follow a geodesic through that curved space-time. Your geodesic is a path through time. You're trying to move forward in time. But the curvature of space-time bends your path inward toward the center of the Earth. If nothing stopped you, you'd fall. You'd accelerate inward following your geodesic. But the ground is in the way. The ground is made of matter, and matter resists being compressed. The atoms in the ground push back. The ground exerts a force on you, an upward force. And that force is what you feel as weight. You're not being pulled down by gravity. You're being pushed up by the ground. Gravity isn't doing anything. Gravity is just the shape of space-time. The ground is what exerts the force. This is the opposite of the Newtonian picture. Newton says gravity pulls you down and the ground stops you. Einstein says space-time is curved and the ground pushes you up. Same result, completely different mechanism. Here's another way to see it. Astronauts in orbit, they're weightless, floating. Newton would say they're still being pulled by Earth's gravity. They're just in free fall. And that's true in a sense, but Einstein would say they're following a geodesic. They're moving through curved space-time with no forces acting on them. The curvature of space-time around Earth bends their path into an ellipse. They orbit, not because something is pulling them, but because they're following the natural geometry of space-time. There are no forces on them. They're in an inertial frame, true free fall. That's why they feel weightless. There's no force acting on them. Contrast that with you standing on the ground. You're not in free fall. The ground is pushing on you. You're being accelerated upward by the electromagnetic force between the atoms in your feet and the atoms in the ground. That's the force you feel. That's weight, not gravity. The electromagnetic repulsion between atoms. Gravity itself exerts no force. It's just geometry. So why does any of this matter? Why should you care whether gravity is a force or a curvature? Because it changes everything. It tells you that space and time aren't a passive stage where events happen. They're dynamic. They bend. They flex. They respond to matter and energy. And that means the universe itself has a shape, a geometry, and that geometry evolves. The universe expands. Space-time stretches. Black holes form. Gravitational waves ripple through space-time like waves on a pond. We detected gravitational waves in 2015. Two black holes colliding 1 billion light-years away sent ripples through space-time, and those ripples reached Earth. We measured them. Tiny distortions in space-time itself, stretching and squeezing space by less than the width of a proton. But we detected it, and it matched Einstein's predictions exactly. Gravity isn't a force. It's the fabric of reality itself, bending and flexing and rippling, and we can measure it. Here's the uncomfortable truth. Your intuition is built for a world where gravity is a force, where up and down are absolute directions, where time flows the same for everyone. But that's not the universe you live in. You live in a universe where time is relative, where space curves, where gravity is geometry. And your brain wasn't built to understand that because your ancestors never moved fast enough or got close enough to black holes for it to matter. So it feels wrong. It feels like word games or abstract mathematics. But it's not. It's reality. And every experiment we've ever done confirms it. GPS works. Gravitational waves exist. Black holes bend light. Mercury's orbit precesses. All of it. Predicted by Einstein. Confirmed by measurement. Gravity isn't a force. It never was. Newton gave us an approximation that works at human scales. But Einstein gave us the truth. And the truth is stranger and more beautiful than anything Newton imagined. You're not standing still right now. You're racing through time at 299,792,458 meters per second, the speed of light. The ground is pushing up on you, stopping you from following your natural geodesic. And the earth beneath you is curving space-time, creating what you feel as weight. That's not metaphor. That's physics. That's reality, and it's magnificent.